to start recording. Okay, thanks.
Thanks. So, welcome everybody. We start the session with Dr. Pedro Liendo from DAISY, and he's telling about bootstrapping holographic defect correlators. Thanks, Pedro.
Okay, you can hear me then.
Yes, very well.
Okay, so today, thanks the organizers for the invitation. And today I'm going to present recent work that was done with Julian Barra and Aleix Jimenez Grau. Julian is a grad student in Berlin and Aleix is a grad student in Hamburg. And I usually start my talks with some motivation, but this is a full conference on conformal field theory, defects, and supersymmetry. So I think we all agree that these are interesting topics that should be studied. So let me save 1 or 2 minutes by just jumping straight to the main setup of this talk. And so today we're going to study half-BPS observables in N=4 super-Young males. And observables in this talk means both local objects, local operators, but also extended objects and or defects. So the half-BPS in the title is because we're going to consider a special class of operators, both local and extended, that preserve half of the symmetry, half of the supersymmetry of the configuration. So when you put an extended object, right, you break some of the symmetry of your system. However, for special classes of operators, I mean, even though you will break the full PSU22/4 symmetry of N=4 super-Young males, you can choose some operators that will preserve basically half of it. So even though we will break some of the supersymmetry in our setup, we will still preserve an OSP4/4 subgroup. So this will be the main setup: 2 local operators in the presence of an extended object. And as we will discuss with more detail later, this configuration is kind of analogous to 4-point functions in CFTs without defects. So then let me introduce you the main characters of our story. So we are going to consider a line defect, a Wilson loop, Wilson line, which is supersymmetric. So there is this extra coupling to one of the scalars, to one of the SO6 scalars of N=4 super-Young males. So this is our extended object. And our local operators are going to be these chiral primaries, which are single traces of the SO6 scalars, and they sit in symmetric traces representation of the R symmetry group. And these objects are protected; they don't receive quantum corrections. They're conformal dimensions, and are among the most classic observables that you can consider in N=4 super-Young males. So Wilson loop, of course, are fundamental in localization, right? You can calculate the expectation value exactly for any value of the top coupling and the rank n of the gauge group. And these chiral primaries have also played an important role in holography. They were used by Witten in his original ADS-CFT paper, the 3-point functions, in order to match with Kaluza-Klein modes in supergravity. And in particularly in recent years, 4-point functions of these guys have been studying relentlessly using the bootstrap approach, and people have understand how they work at strong coupling, and they have also calculated corrections that correspond to either supergravity corrections or string theory corrections, 1/n corrections in n, which correspond to quantum gravity. So I think it's safe to say that you see my mouse, right? The pointer, or not? Someone say yes.
Yes.
Okay. So I think it's safe to say that there are probably hundreds of papers on this subject, right, on the Wilson loop, especially since the advent of localization. And there are probably also hundreds of papers about correlators of these chiral primaries. However, and perhaps surprisingly, a lot less work has been done studying putting these two beasts together. So this is probably the canonical extended operator that you think of when someone talks about n equals for super Young Mills. And these were the canonical example of local operators that we consider in n equals for super Young Mills. However, correlators with both these objects, both local and extended, have received a bit less attention. Now, one-point functions have been studied. However, these are completely fixed by kinematics. So the coordinate dependence of this object is fixed by symmetry. Now, there is an overall coefficient, of course, that is dynamical, but that overall coefficient can be fixed using localization. So this object is kind of fixed by symmetry. Now, this object is the first one that is like truly dynamical. So this object depends on conformal invariance, is not fixed by kinematics, and it is a function that in principle you need to calculate. So in this talk, we're going to concentrate on this guy, which is, as I said, the first like truly non-trivial correlator in which you have local and extended, when you have the Wilson line and local operators. So let's discuss in a bit more details the main characters of our story. So this is going to be our Wilson loop, where this theta angle defines some direction in our symmetry space. And our chiral primaries, where in this talk, we're gonna just look at phi square. Sometimes people call this the 20 prime because the symmetric traces representation of SO6 with two indices has dimension 20. So I would call it also the 20 prime. And if you're familiar, for example, with the work of Dolan and Osborne, this supermultiplet is sometimes denoted by this funny symbol, and the 0 to 0 are just SO6 Dinkin labels. So the 20 prime in SO6 Dinkin label is basically the 0 to 0 representation. So 20 prime, the 0 to 0, or phi square. Most of the time, I'm just going to call it O2, the 2 corresponding to phi square. So this is the correlator that we're going to focus on. It's the 2-point function of the 20 prime, which, by the way, is the multiplet in which the stress tensor sits. So it's the one guy that we know it's there in n equals 4 super Young Mills. And the correlator is not fully fixed by kinematics, but depends on some invariants. So C and Z bar are spacetime invariants that we're going to review in 3 minutes. W is an R-symmetry invariant because we have indices in this story. So let me first, because it's the new ingredient that we have when we do SUSY, let me tell you a bit about what this W is. So as you see, I am contracting the R-symmetry indices with auxiliary vectors. This is because I don't like open indices, so I rather contract with these auxiliary vectors, and then my correlator will depend on this U, but I will not have annoying Kronecker deltas. And so let's say if you're calculating this function perturbatively, for example, you can contract the two local fields among themselves, and then you're going to get a dot product of these U vectors. You can also contract the fields with the Wilson line, and then you're going to get dot product of the U vector with theta, and then you can also have this configuration. So the main message is that our correlator, it's basically going to be a polynomial of this variable after extracting the prefactor. So because I am contracting these R-symmetry indices, it is convenient for me to define this omega variable, because then the correlator is basically just a polynomial in this omega variable. I mean, here I define this sigma to make it explicitly that it's a polynomial. But so the upshot, the message is that if I had open indices, basically I would see tensor structure here, Kronecker deltas. I don't like open indices, so I contract my open indices, and so now I have a polynomial in omega. So basically these 3 powers of omega, they just capture the different R-symmetry channels. So there's nothing mysterious, this is like standard technique. Now, what will be important though, is that the R-symmetry is not a flavor symmetry that commutes with the conformal group in this setup. The R symmetry is part of the superconformal algebra. So these three R symmetry channels, right, that correspond to different tensor structures are not all independent, but they are related because of conformal symmetry. And the dependence in the way in which these three channels are related can be written very elegantly in a set of equations that is called the word identities, which take this very elegant form. So you see, that's why I define this omega, because it's very useful. These three channels are not all independent, but by imposing that our full correlators satisfy this condition, this is basically the statement of superconformal symmetry. And this tells us that then F0, F1, and F2 are related to each other because these equations have to be satisfied. So this will be one of the important equations in this talk. And as I said, this is what we're after. We want to calculate this correlation function. Now, just to tell you that we study this object at weak coupling using standard Feynman diagram techniques. So if you want to see how weak coupling calculation goes for this guy, look at this paper. But today, we're going to study this guy at strong coupling. That's why the title of the talk says holographic. So we're going to study this guy in the regime where holography is valid. And of course, we don't have Feynman diagrams to do the calculation. Today, we're only going to use bootstrap techniques. So let me then give you a crash course on the basic tools, basic analytical bootstrap tools that we're going to use in order to calculate this guy. So this is the goal for today. So whenever you have a defect, as we already discussed, you break some of the symmetry. So without the defect, you have a full conformal group. When you add a defect, you break some of the symmetry, and it is very easy to see from the picture, right? So we have a conformal, a 1D conformal symmetry parallel to our Wilson line, but we also have some rotational symmetry around the defect. So we break our SO4,2 down to a 1D conformal symmetry times a rotational symmetry around the line. And the nice thing is that even though we broke some of the symmetry, this is still strong enough in order to use bootstrap techniques. So 1-point functions now of local operators in the presence of a defect are non-zero. They are fixed by kinematics. Xi here is the orthogonal distance to the defect, and this new object here is a 1-point function, and this is new CFT data, which is in a sense related to the defect. So you cannot prove this 1-point function by looking just at correlators of local operators. So this is one of the new piece of new data that you get when you add defects into the configuration. 2-point functions are not fixed by kinematics, but they depend on two invariants, which I'm calling Z and Z bar. And here you can see again what I already announced, that then this configuration, 2-point functions in the presence of a defect, is kind of similar to 4-point functions in standard CFTs. Now, these two cross ratios have a very cute geometrical interpretation. So this red cross is the defect coming out of the page. And now we have our two local operators. Using conformal symmetry, you can always put one of the operators at 1, 1. And then the other operator, you can put it on a plane, on a common plane. And then these cross ratios, Z and Z bar, this invariant, in this, you can interpret them basically as the coordinates of the second operator. So we have the defect at the origin, we can put one operator at 1, 1, and then the coordinates of the second operator are basically the two invariants that appear in the correlator. So again, being analogous to a 4-point function, we can write a crossing symmetry equation for this correlator. And for that, we need the operator product expansion. So we have the standard bulk OPE, in which the product of two fields can be written as an infinite sum of operators at a single point. But when you have a defect, you have this extra tool in which a local operator can be written as an infinite sum of excitations that live on the defect. So that's why I put a hat here. This operator is constrained to live on the line. And then with these two operator expansions, we can write the analogous of crossing symmetry. So you can fuse the two scalars together. Remember that this is the correlator that we want to study. So we can just fuse them together using the bulk OPE. And then we bracket this equation. And so when you bracket here, you get a 1-point function coming from this operator O times the 3-point function from the bulk OPE. And this picture here, this is what we call a conformal block, and it's basically a function that captures the contribution of O and all of its descendants. You can play the same game with the bulk to defect expansion. Each of the fields, you send them to the defect, and then you bracket the remaining 2-point function. And again, you get now the square of these bulk to defect couplings, and this picture here is what we call a conformal block, and it captures the contribution of O hat and all of its descendants. Now, I should point out that these functions are kinematically fixed. So we know them. They are basically hypergeometric functions. On the defect side, they are literally 2f1s, products of 2f1s. On the bulk side, you can think of them as some sort of generalization of hypergeometric functions, but the point is that they are fixed, they are known, and we understand them very well. Now also look that the data that appears on the two channels is not quite the same. So on the bulk channel, we have bulk data. So they are labeled by the conformal dimension and the spin. So this is the spin that we know and love, that we're familiar with. But on the defect side, the operators are labeled by conformal dimensions, but of operators that are constrained to live on the defect. So that's why we put a hat. And this S is, again, sort of a spin variable, but it's not the spin that we know and love. It's this new spin variable, right? I told you that when you have a defect, you have rotations around the defect. So we call these rotations transverse spin, and this is what this variable S is. It is the spin associated to transverse rotations around the defect. So this is crossing, and as you know, the goal of the bootstrap is to try to use this equation in order to solve for the CFT data. So then now that we reviewed the basic tools of the defect bootstrap, let's go back to our supersymmetric example. So what I just proved to you is that the correlator has two different decompositions. It has the bulk channel expansion, so that one would be this one. But you can also write it on the defect channel expansion. So that one would be this one. And again, because we're doing SUSY, remember that we have to add this extra variable, which is basically polynomial. And so our blocks are really super blocks. So this F delta comma L is a bosonic block. So this one would be this picture. This one is a defect block. This one would be this picture. But because we're doing SUSY, our super blocks are a finite sum of bosonic blocks. So these objects here are finite sum of bosonic blocks. And these H, you can think of them as R-symmetry blocks. So they capture the R-symmetry quantum numbers associated to SO6 or to SO5, depending on which channel you are. But again, these are basically polynomial functions. So then here we understand something very important. So this is what we're after. We want to calculate this 2-point function. And here I have basically 3 representations of the same object. So first, you can calculate the 2-point function by independent means. I mean, if you are good at Feynman diagrams or holography, etc., you can just calculate F and just give it to me and everybody's happy. Now, with this block expansion, we have 2 other representations. And if you know the bulk data, basically these 3-point functions and these 1-point functions, then you can perform this sum, because this is a function that we know. As I told you, is a sort of generalization of hypergeometric function. So you can just calculate this data and perform this sum, or you can calculate the bulk to defect data and also perform this sum. So all these methods should give the same result. So in this talk, we're going to go after these guys, the bulk to defect data. So we're going to bootstrap this correlator, and this is how we're going to do it. We're going to calculate the bulk to defect data using bootstrap techniques, and then hopefully we're going to perform this sum, and we're going to land with the strong coupling correlator. And now, how are we going to do this? So we're going to use analytical bootstrap techniques. And let me just give you a flavor of how these analytical bootstrap techniques work. So consider, for example, crossing. So the idea is, for example, to take some limits on the right-hand side of the equation. So you can take some special limit. Imagine that you take some special limit on the right-hand side of the equation, such that you see some singularity. Let's say some 1 over x. So if you take some limit on the right-hand side of the equation and you see some singular behavior, this singular behavior on the right-hand side will put very strong constraints. Sorry, this is the left-hand side. If you take some limit and you see some singular behavior on the left-hand side, this singular behavior will put very strong constraints on the right-hand side, because the spectrum and the CFT data will have to have some particular form in order to reproduce the singular behavior that you're seeing on the left-hand side. So that's basically the main idea behind the analytic bootstrap. So that was the analytic bootstrap in 30 seconds. But the nice thing is that this intuition, right, of trying to reproduce singularities on one of the sides of the equations by fixing the data on the other side, was beautifully captured by an inversion formula, which is the technique that we're going to use. So we're only going to use bootstrap techniques, but as I said, we're going to bootstrap a strong coupling correlator. So even though we're not going to do holography in this talk, let me just give you an intuition of the object that we're going to bootstrap. So we want to study this correlator at strong coupling, and there is a holographic description. So if you are good at holography, in principle, you can calculate this object using Witten diagrams. So the leading correction in terms of Witten diagrams in this one, which is just a disconnected component, so this is just the identity contribution, so it's kind of trivial. So at strong coupling, the natural parameters that you get when you look at this expansion are lambda over n squared and 1 over square root of lambda, where lambda is the top coupling and n is SUN, the rank of the gauge group. So this part is disconnected. It's kind of trivial. It's just the identity. This part is given by this diagram. So this is a 1-point function. But as I told you already, 1-point functions in the presence of the line are fixed by symmetry. So this contribution is basically the square of a 1-point function. So it's also kind of trivial, also fixed by symmetry. This guy is given by this diagram, and this is what we're after today. So this one is the first one that is not fixed by symmetry and that it's truly dynamical. So if you want to see the holographic setup for this 2-point function that we're going to calculate, you can look at this paper. And if you're good enough, again, you can try to calculate this diagram. But that's not what we're going to do today. Today, we're going to do the bootstrap. And as already announced, the idea of the analytic bootstrap is to fix the data on one channel by looking at singularities on the other channel. And this idea was beautifully formalized by Caron Huot in terms of an inversion formula. So let me tell you what this inversion formula means. So this is what we want. This is the bulk to defect data. So if we get the bulk to defect data, we can resum, we can do the sum, we can do the block expansion sum and then obtain the correlator. And the idea is that the CFT data is given by residues and poles of this function B, which can be obtained from a certain discontinuity of the correlator around z bar equals 1. So this J is a kernel. It is a function that we understand very well. So after you calculate the discontinuity of the correlator, you just multiply by the kernel, do these integrals, and then you can extract the CFT data by looking at the poles and the residues of this function. Now, there are two important comments that I want to make here. And is that, remember that f of ZZ bar is what we're after, right? Is the correlator that we want. So here you could complain immediately about circular reasoning, right? You can tell me, okay, you're after f and you want to calculate f by obtaining the CFT data, but of course you don't know f, right? So how are you going to obtain b if you don't know f? And that is absolutely true. We don't know the correlator. This is what we're after. However, the formula does not need the correlator, but it needs the discontinuity of the correlator. And this is one of the reasons why this formula is so powerful, because the correlator might be a complicated object, but the discontinuity of the correlator, is a simpler object. And so what happens in practice is that in many favorable situations, even though we do not know the correlator, we do know its discontinuity. And thanks to this inversion formula technology, the discontinuity is all we need to extract the defect data. And in the strong coupling setup that we are going to study today, it is actually an example in which we don't know the correlator, but we do know the discontinuity of the correlator. So that's the first comment. The second comment is what I put on red here, is that this formula will give you the CFT data for all the delta hats and all the spins, with a small caveat that it might not give you the data for some low values of the spin variable. So this is a technicality that if you want, we can discuss later, that comes from the derivation of this formula, but the message is that the correlator that you obtain by using this discontinuity technology will be correct, except for maybe some low spin ambiguities. So you will get the correct CFT data and therefore the correct correlator, but there might be some ambiguities only for very low values of the spin. So this is an important caveat of this whole business that will play a role later. But again, you will get most of the CFT data correct, but there might be some low spin ambiguities in your final result. So then let's, I should say, of course, that if you want to interrupt me, you can just do it and unmute and ask.
Pedro?
Yes.
Can I ask a question?
Yes.
Yeah, this S star as you know, we couldn't fix it
Yes.
on general ground.
Yes.
Is there some argument, some better argument for this holographic correlator that tells you a priori that it has to be finite?
Yeah, we don't at the moment. So first, nothing that I'm going to say is rigorous. First, we expect that in supersymmetry, things should be a bit better, right? Because operators are related by the action of supercharges. So we expect that maybe a low-lying spin is somehow related by supersymmetry by a higher spin. Now I'm going to show you at the in a couple of slides what we did, and then you tell me if I convince you. But no, we don't have a proof of this S star, but experimentally we found that it seems to be 2 in this case. So it seems that the only ambiguities that we have in this setup is for spin 0 and spin 1, which again, I don't know. Seeing that we are in a supersymmetric example, it doesn't sound too I don't know, too extreme. Okay, but yes, this will play a role and we will discuss it. So then let's discuss how do we calculate the discontinuity of F. So this is what we're going to do. I announced we're going to go after the defect data. And in order to calculate the discontinuity of F, we are going to write F as a bulk channel expansion. So we don't know any of these coefficients, but let me write F as a bulk channel expansion and see what happens. So this is my correlator, which again, I do not know because all these coefficients are unfixed, are dynamical. But now the key property, look that I wrote it in a very suggestive fashion. So 1 is the identity. Then we have a short operator, which is the 20 prime itself. So this is the block associated to the 20 prime. And then we have an infinite number of operators that appear in this sum that are mostly long operators that are not protected. But the key property is that all of the operators that appear on this sum have conformal dimensions of the following form. So when operators have conformal dimensions of this form, basically twice the external dimension plus L plus an integer, we call them double trace, because they are literally operators that are contracted by double traces of the external guy and acting with derivatives. And this is standard when you consider holographic CFTs. So when you have these holographic theories at strong coupling, the vast majority of the spectrum is basically double trace guys. So they have conformal dimensions of this type. Now these double trace dimensions will get corrected by anomalous dimensions, but at the order that we're working in this paper, these anomalous dimensions do not contribute. So at the order, and this is the key property, at the order that we're working, all these guys are basically double trace operators. And why this is such a big deal is because the discontinuity of double trace blocks is identically 0. Again, if you want, you can consider this a technicality of this definition, but it is a fact that when you calculate the discontinuity of a conformal block that has exact double trace dimension, then you get a big fat 0. But then this is remarkable because I promise you that F is a complicated object, but the discontinuity of F might be a simpler object. And here we see it explicitly. F is this infinite sum of blocks, but when you apply the discontinuity, you basically kill everything. And at the order that we're working, the identity is there, but this one again is one order less. So this one we already knew. We already know its form, but at the order that we're working, basically one operator contributes to the discontinuity. And as announced, we know these functions. These are basically generalizations of hypergeometric functions. So the message then is that we can reconstruct the full CFT data from a single conformal block. So amazing. So we're reaching basically the end of the talk. So let me tell you how it works. So at leading order, we have, for example, this defect family with this bulk to defect OPE coefficients. And now using our inversion formula technology by inverting a single conformal block, superconformal block, we can obtain now the anomalous dimensions and we can obtain corrections to the OPE coefficients. And now we can do the sum. So now our correlator is this infinite sum of basically hypergeometric functions with these coefficients that come from the inversion formula. Now, the remarkable thing is that this sum turns out to be, the result turns out to be shockingly simple. It is just a log and a rational part. And again, I mean, here I would like to stress the fact that we have an infinite sum of hypergeometric functions. So when you add an infinite sum of hypergeometric functions, anything can happen. So the fact that this crazy sum gives such a simple result, it's probably a strong indication that we're on the right track. And remember that we have 3 symmetry channels, so we apply the inversion formula to the 3 channels. The other channel is also extremely simple. And then the final channel, actually, because this is a short block, is that it does not probe all the channels. So in the final channel, we don't even have a discontinuity, so we get 0. So this is the result that we get by inverting a single superconformal block. Now there is one problem, and is that this result, although elegant, is actually not supersymmetric. So recall that at the beginning of the talk, I told you that the word identities are sacred. So if this thing if we want a supersymmetric correlator, it has to satisfy the word identities, and this object does not satisfy the word identities. And then now comes the warning, and what Marco just asked is that we know in this discontinuity business that there will be ambiguities related to low spin values of the spin. So then what we did, we found a minimal prescription that will allow us to supersymmetrize our correlator. So we basically added spin 0 operators to the F1 channel, and we added spin 0 and spin 1 operators to the F2 channel. And then we imposed the supersymmetric word identities, and we also checked consistency with the bulk expansion, because this is, of course, the moment you start adding things, you might screw up our basic assumption about the holographic spectrum, that it does not have anomalous dimensions. Now here again, I'd like to point out that we are going to add an infinite number of operators with spin 0, with arbitrary coefficients. So we're being very agnostic about these ambiguities. So we're going to add an infinite number of operators with unfixed coefficients, and then we're going to impose the word identities. And it turns out that the word identities, even though simple looking, are so powerful that the result is actually completely fixed without any free parameter. So let me then show you our improved final result for our holographic correlator. Now this result is fully supersymmetric, and as you can see, there are no free parameters apart from an overall coefficient that can be fixed using by comparing with localization. So this is the end of the talk, and again, let's not lose track of what we were doing, of what we were planning. This is our prediction. So whomever makes these holographic calculations explicitly for this diagram, this is the result that you should get. So then our result passes several consistency checks. So it still has the correct discontinuity, even though we added these ambiguous spin zero operators. It is consistent with localization, and this is very important. So let me expand a bit on it. So now we have the full correlator, and you know that by using the operator product expansion, we can extract the data. So in particular, we can extract some of the data, CFT data that you can extract from this correlator can be compared with localization. It's a handful of coefficients, 3, 4, 5, but we find a perfect match. So you see, we expand this thing in bulk blocks and we expand this thing in defect blocks, and some of those coefficients have been calculated using localization, and we find a perfect match. But let me also stress the fact that we have the full correlator, so we can also extract an infinite number of non-protected CFT data that is not captured by localization. So that's why in the Bootstrap, we care so much about correlators that depend on cross ratios, because this correlator is not that it looks elegant. Thanks to the operator product expansion, I can extract now an infinite number of CFT data. A handful of them I can compare to localization, but there is an infinite number of non-protected data that is new and we can extract from here. It satisfies the word identities as pointed out, and it has a sensible operator expansion in both the bulk channel and the defect channel. And it is not easy to find a function that satisfies all of these constraints. So let me then discuss conclusions and future directions. So basically, we bootstrap correlators of Half-BPS operators at strong coupling in the presence of a defect. In this talk, I just talked about trace phi squared, but in the method is completely algorithmic, and in the paper we did it also for phi squared, phi cubed, and phi fourth. And the result is always the same. The result is, the result is always completely fixed without free parameters, and again satisfy all these consistency conditions that I listed here. Now, it would be interesting to do the explicit holographic calculation. We did the bootstrap, but now that we know that the result doesn't look that complicated, right? It's just logs and rational. Perhaps we should just look at these Witten diagrams and calculate them and confirm our prediction. But another extremely interesting thing that one could do is to study this type of correlators in mailing space. And the reason is that without defects, so you see, I've been trying to sell that this correlator is not that complicated because it has logs and rational. But what we have learned in n equals 4 super-Yang-Mills strong coupling is that this type of correlators, they look even simpler when you study them in mailing space. In particular, in n equals 4 without defects, these holographic correlators are just rational functions of the mailing variables. So it would be interesting to see how our correlators that we obtained in position space, how do they translate in mailing space? And maybe they look even simpler. And then if that's the case, then we can be a bit more ambitious. For example, we can start trying to go to higher orders if indeed the mailing space is a simpler language to describe these objects. And for example, I've noticed, even though I'm not expert, that a huge deal is played by the flat space limit. So when you consider this type of correlators without defects, the flat space limit puts strong constraints on the mailing amplitudes. Is there an analogous of the flat space limit in our defect setup? And could we use it, for example, to put constraints on our amplitudes? And again, something important, and also to relate to Nadav's talk on Monday, that all the techniques that we use were basically non-Lagrangian. They were just analytical bootstrap techniques with some input coming from the holographic spectrum. And for example, the defects that Nadav described on Monday, these half-BPS defects on the 2,0 theory, I think all of the techniques that we discussed in the talk today should also apply for the defects that we saw in this Monday talk. So anyway, it's 41 minutes, so let me finish here. So thank you.
Okay, thanks to Pedro for the very clear and beautiful talk. You have been in perfect timing, so there are space for some questions, at least 5 minutes, I guess. Then we can go to the coffee break. So, are there questions in the audience? Comments?
Hello, I just have a question.
Yes.
Okay. Yeah, just regarding the limit on S star, is it, I mean, presumably the theory doesn't have any like ambiguity. So is there an understanding of why you get this?
Yeah. It's I mean, again, it's a technical question, and again related to what Marco asked. So obviously the theory does not have any ambiguity, but the point is that this formula is not perfect in that sense. So this formula gives you the CFT data, but only for some values of S. There is some low values of the spin, which are just not captured by this formula, basically because they are operators in which when you agree the discontinuity, you just kill them. Now, in the standard CFTs, without defects, Caron-Huot, based on previous work by Peredones and friends, you can actually give a value for this S star is actually 2 without defects. In our defect setup, we don't have, as of now, a proof of what is the value of this S star, a general bound for this S star. So what we found experimentally is that in this case, it seems that S star is 2. And my argument is that we managed to supersymmetrize our correlator just by adding spin 0 and spin 1. And then we checked all these consistency checks, especially the ones with comparing with localization, which are highly non-trivial. So I think in this example, S star is probably 2, but we don't have a general proof of what this star is in a general defect CFT.
Okay, thank you.
Please.
Hey, Pedro. Following
Hi.
Maxime's question a little bit. So was there some intuition for why you added these 0 and 1s just to certain of the Fs and not all of the Fs? Or
Yeah, I think again the intuition is so I think the reason is that we considered the minimal prescription. And I think the intuition again is probably supersymmetry, right? Because if I add a spin 0 guy here, then by acting with supercharges, I will probably generate a spin 1 guy. So if you put spin 0 and spin 0, it just doesn't work. So you need to put spin 0 and spin 1. And I think that's, I think that the intuition is probably supersymmetry. That's why we need to add spin 1 here.
Carlo?
Yes.
Carlo, ask.
Hi, Pedro. Thanks. But can you remind me? So you agree that if you know F0, then F1 and F2 are always fixed by word identities?
Yeah, that's an important comment by Carlo. So, and maybe you're right, and maybe that's what we did. So for the experts of word identities is that these equations, yeah, what Carlo says is in principle you can solve them, and what you learn is that the high star symmetry channel basically fixes them all. Now, in n equals 4 Supereigen-Mills, this relation is algebraic. So if you know the high star symmetry channel, you can obtain F1 and F2 just by multiplying by functions of the cross ratio. In this case, is a bit harder because solving these word identities is just a bit more complicated because the channels are not algebraically related. But yes, Carlo might be right. So in this paper, we did it the stupid way. We studied each channel individually, but Carlo might be right that there might be a more elegant way in which you rephrase everything in terms of just the F0 channel. And then by, let's say, applying some differential operators, you can reconstruct the other two channels.
My question was different. So I understand that solving explicitly is very hard.
Yes.
You take F0 and extract the OP coefficients.
Yeah, but the problem,
sum the blocks.
Yeah, the problem, if I remember correctly, is that of course there are short multiplets that do not prove all the channels. So I think that might also, I don't remember now exactly if this is the case here, but I think you don't prove all the OPE coefficients with just the F0 channel because some short multiplets only prove 2 of the 3 channels.
Okay, just a curiosity, Pedro. When you say that localization fixes a coefficient, you had in mind to put some of the external operator, I mean of the bulk operator, in some favored BPS situation that can be directly computed by localization.
Yeah. So basically, I'm saying this guy. This guy, in the presence of the Wilson loop, this one can be localized. So this is the 1-point function of O2. And that's the coefficient. It's the only unknown coefficient in our formula. So I told you that you just need the discontinuity of this guy. So this 1-point function is basically can be localized. And the 3-point coupling, it's known to not renormalize. It's just actually just 1 over n basically. So basically this is the overall coefficient. So this is what you get from localization. This is the 1-point function. And the 1 over n is just the OPE coefficient. So yes, it's a half-BPS operator in the presence of the half-BPS line. So these are known for all values of lambda and all values of n.
Yeah, so you don't use a result for the second correlator in your page from localization.
Well, but that's the point, that this correlator depends on invariants. Okay. So this correlator cannot really be localized. Now, there is one favorable, as you said, kinematical configuration in which you can localize this guy, and it's actually very elegant. In terms this 2-point function depends on 3 invariants. When you set these 3 invariants equals, so when you put C, C, and Z, this is the kinematical configuration that can be studied by localization, basically. So if you put C equals C equals C, these 3 arguments, this correlator goes to a constant, and that constant can be localized. But this is something that I would like to stress. When people study these correlators using localization, they are literally probing 1 point in a 3-variable function.
Okay. Thanks a lot. We have last question by
Can I ask one more question?
Lorenzo. So, Lorenzo.
Yeah. Hi, Pedro.
Hi.
So I wanted to ask what's the status for other defects?
Yeah, I
surfaces,
actually
boundaries?
had, sorry, I'm gonna say in 1 minute. I actually had an extra slide.
This wasn't prepared, I swear.
This was, so to connect with Nadav's talk, what about 2 local operators outside these 2,0 defects? So in this paper, this guy studied correlators on the defect and look at the word identities that they satisfy. Now, these are very similar to the ones that I consider here, right? They call it alpha, I call it W, but these are operators on the defect. So most likely, this guy, so 2 local operators outside the defect, they probably satisfy a very similar word identities, like the ones that we saw in this talk. And if that's the case, then we have a really nice long-term bootstrap problem. First, obtain the word identities for 2 local operators outside the defect that Nadav presented. Once you have the word identities, you can calculate the conformal blocks by solving these word identities in terms of a finite sum of blocks. And then when you have the blocks, you can just apply the discontinuity technology, because these comments regarding the holographic spectrum, they are not specific to N=4 super Yang-Mills. They are truly general. The fact that at strong coupling, most of the spectrum is exact double trace. So I think this is doable. And again, ABJM, which you are the local expert or one of the local experts, I haven't thought about it, but again, I wouldn't be surprised.
I was thinking more of other codimensions for N=4.
Yeah. So I think there are also surface defects. I think you break a bit more SUSY. I mean, it's not OSP4/4, it's some PSU2/2 squared. Yeah, I haven't thought about it, but again, I think the key property, it's always that the bulk spectrum is exact double trace. So I think perhaps this thing is also general. It's also true for more general defects in N=4 super Yang-Mills.
Okay, thanks.
Okay. So probably we can stop here, and maybe there will be more discussions in the discussion session later, where I thank again Pedro for the very clear talk, and we will find ourselves in 10 minutes, I guess,